Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, hello, good afternoon. My name's David Holmes. I'm in the Civil and Environmental Engineering Department at MIT. And today I'll be talking about mitigating the energy crisis using simulation for enhanced oil recovery. And basically that's just a nice way of saying that we're making simulation models to increase the amount of oil we can get out of oil reservoirs. Now, firstly, I'd like to acknowledge my co-authors, Professor John Williams, also at MIT, and Dr. Peter Tilker of the Schlumberger Dell Research Centre. So I guess everyone here is aware of the current energy crisis, the problem that we have with oil prices and the actual ability to get oil out of the ground, dependence on foreign oil, those sort of concepts. I guess a lot of you may not be familiar with the fact that during the oil recovery process we leave a significant amount of the oil in the ground. And so being able to improve the amount of oil recovered is really important to our cause. So the general theory of the work that we've been doing at MIT is to generate numerical simulators to model the oil field type dynamics with the hope that we can develop enhanced oil recovery techniques. And I guess the real complexity of the physics at play dictate that any simulator used for this type of circumstance needs to make the most of the computational resources at hand. And with the move of companies like Intel and AMD into the multi-core type architectures, it's critical that simulators are able to make the most of those as well. And that's some of the primary focus of our work that I'll be presenting today. So just a brief outline, I'll discuss what enhanced oil recovery is and the need for it. Then I'll briefly go over the simulation framework for multi-core that we've developed, and then some of the testing and applications on that framework. So during the oil recovery process, through primary development, it's possible to get about 20 to 40% of the oil out of the ground. So primary development is basically drill and pump. Existing enhanced oil recovery techniques such as water flooding and gas injection, etc., can optimistically recover an extra 10 to 20%. And basically what this means is you're leaving almost half the oil in the ground. Now, that can tend to be a product of, firstly, the fact that these oil reservoirs are upwards of a kilometre underground, so our ability to actually do measurements and understand where that is severely hampered. And also, if you look at this picture just here, the oil isn't just in a big chasm full of oil. It's actually infused into the reservoir rocks in pores, pore spaces, pore throats, so it's very, very tricky to actually get this oil out of the ground. And being able to simulate that is one of the major things we want to do. So the Department of Energy estimates that using next generation enhanced oil recovery techniques, the US alone could stand to generate an additional 240 billion barrels of recoverable oil resources, which at current consumption rates is about 30 years supply. So it's very significant. And the ability to generate numerical models to help develop these enhanced oil recovery techniques is very important to maintain our way of life. So some of the modelling challenges that we face in the oil reservoir, it's a multi-phase problem, so oil, water, gas, you've got deformable granular media, so all of these things we'd like to be able to model to better understand the dynamics at play. As I was discussing, the actual measurements that we can do on the oil reservoir is fairly limited, and the ability to interpret and calibrate those tests is critical. So we can develop those through models. Hydrofracking is a technique that's been used to some success and increasingly thought of as a decent method to increase the permeability of rock. So high pressure water will fracture the rock, hopefully increasing the permeability and the flow rate of the oil, but being able to work out the best way to do that and whether it's actually going to have an advantageous effect is very important. Sand production and borehole type collapse, so moving fluids will erode the media through which they're flowing and may change the actual permeability of the rocks. Something that's not necessarily enhanced oil recovery, but it's in a similar vein, is carbon sequestration and hydrate mining. So the sort of multi-phase modelling that you'd be doing for oil recovery, you can also use for some of the more environmental impact type modelling, such as carbon sequestration and hydrate mining. And as I discussed, it's pretty important for these techniques to be able to make the most of the computational resources. So programming these for multi-core and multi-machine is critical, and today I'll be mainly focusing on multi-core. So to actually implement an application in parallel, generally you make use of concurrency packages. The conventional methodology for numerical simulation is generally cross-machine type parallel implementation, and MPI is generally the concurrency package of choice for that type of application. Now for multi-core, Microsoft has released a powerful new library called the Microsoft Concurrency and Coordination Runtime, which is distributed as part of the Microsoft Robotics Studio CTP at the moment. And this is the base package that we've been using to develop our parallel framework. But the similarities between many of the types of simulation codes that you can use for these type of applications dictate that there is further generalisation, and some of the complexities of those techniques need to be addressed. So the second point I've got here is some of the challenges to concurrency. The first three there, synchronisation, thread safety and load balance, are fairly applicable to most parallel applications, and I won't go into too much detail because I'm sure most of you are at least a little bit familiar with those. The bottom part here is challenges which are relatively unique to simulation, and those challenges are spatial reasoning and dynamic evolution of numerical tasks, which I'll discuss just briefly now. So with respect to spatial reasoning, in a conventional cross-machine type application, you'd be dealing with something called domain decomposition, which is effectively, if you've got, in this case, 5 machines, you want to break up the model that you have into 5 distinct parts, send it out to each of the machines, they would process and then coordinate and whatnot. Now, important to remember, you have to have communication between the domains because of the actual calculation. And also, when you choose the size and shape of these domains, generally they're chosen as to being almost exactly the same computational expense, such that you're doing what's called a predictive load balancing. You're assuming each processor is going to take the same amount of time for the same job. Now, for the multi-core type architecture, you're dealing with a shared memory, so there's not that necessity to actually send out physical parts of the model to different machines. You can maintain a single memory source, and so what you could actually do is something like this domain distribution, where each of the calculation points, in this case elements, rather than having to be clumped together, a core can just calculate on that single point as it becomes available to do so. And if you can program that correctly, then you're dealing with an events-based load balance, which is far more superior with respect to processor utilisation. Now, the second point is dynamic evolution of the numerical task. So what's perhaps not common to many parallel applications is that from one time step to another throughout numerical simulation, the number of tasks that need to be calculated can change. So this is just a simple finite element example. What you have is adaptive remeshing in the critical zone. So from one step to another, you'll have more elements or less elements depending on how that evolves. Something like a discrete element model, just 2 conveyor belts going through a hopper. The hopper is the critical region, it's what you're interested in, so as the particles leave that system you can delete them, but you've constantly got a changing number of calculation points that you need to do. And something a bit closer to what we've been working on, which is sort of free surface fluid type flow as an example. If you've got a fixed grid and you're only calculating the grid points where there is fluid, something like a free surface splashing water drop like this will splash up and have several little particles, and so increase the number of cells that you'd be calculating on. So these are non-trivial points with respect to synchronisation and actual implementation of the parallel algorithm. Okay, so we've been using, as I said, Microsoft's Concurrency and Coordination Runtime. I'd firstly like to acknowledge the help of George Chrysanthopoulos and Henrik Nielsen, both of Microsoft, for their aid during the development of this framework. So these are just some of the really simple primary concurrency tools of the CCR that we've been using. So it's a very web services-based application. You've got these ideas of port and receiver. on the port you'll post some message. That message is not necessarily your data structure, it could be a pointer to your data structure. But once that message arrives, this handler will receive that message and then cast a separate thread to process that message. So if you had 10 cores, you posted 10 messages, then you would have 10 parallel threads here operating, which is a really neat way to actually function. Now, this is a schematic of the developed mechanism that we've basically put together for the parallel numerical tools. So some of the tools of the CCR are excellent, but that's basically what they are, they're tools. For numerical implementations, you need a significant amount of programming in that to get what you want, and so we've basically bundled that up in a general sense into a library that's appropriate to most numerical simulation, if not all. The schematic over there on the right is basically the programming model. So a standard programming model might be just a standard master loop, and at every time step you cast out several parallel threads. We've gone more for the master casting out to slave threads here, each of which maintains their own time step, and then there's a synchronization at each time step to maintain the consistency between each of the threads. And this synchronization point can be a thread, it can be peer-to-peer, but we've just chosen a separate thread which we've called the dispatch, not to be confused with the CCR's dispatcher. So the idea of this dispatch is basically that it maintains a stack of data points and it distributes those data points to each of the threads as required. The way it does this is the thread requests a value, receives it, processes it, and loops back around and requests a value again. And the idea is that it's shifting from a push mechanism to a pull mechanism. These threads manage the fact that they need a new one, and in that way then it's that events-based load balancing, which is what I was talking about. So the advantages of this is perfectly load balanced, it accommodates any CPU number, and particularly it accommodates variable CPU efficiency. So it's really important to consider in the multi-core environment, if you've got operating system threads, you've got threads from other applications, you might have a thread for an output function, then those threads can be stepping on the threads that you're actually simulating here, and so it can cause processor redundancy if you don't have that variable CPU efficiency. So that's pretty important. Some of the programming challenges, I'll just go back to that figure. When dispatch is receiving this data, rather than a concept of counting up the data and understanding the number of data points there should be, when dispatch receives this, the thread that's sending the data to it sends a message when it's finished sending everything to it, and dispatch does the same thing to the thread. So when all this data has been used up, it will send a message to each of the threads saying that it's finished. Also, it's important that each of these processes is finished, and so dispatch must take care of that as well. Mainly because if one of these processes is still going when you loop around to the next time step, then you have significant thread safety issues. Okay, so some of the testing and application that we've been doing, we've basically been, when we set out to choose numerical technique, we were looking at the multi-physics, multi-scale type realm for fluid flow, and we ended up squarely in the particle methods. They're taking off in the numerical world. And the benefit is that you can go from sort of up near the physical scale, so macroscopic, finite difference, finite elements, right down to sort of the grain scale, discrete elements, and perhaps even bordering on molecular dynamics type scale. So at the moment we're focusing on the grain scale, but with hope that will spread either side. All right, so this is just testing. This is a 24-core server that we just got recently. You can see that using that dispatch, we've got 100% usage, and that each of these step downs here is a synchronization point. So the synchronization is actually not killing the processor significantly, and we've got fairly almost perfect processor utilization. This is some testing that we did earlier before we received that machine on an 8-core Intel Xeon server. You can see here speed up is near linear. This is for 100,000 to 700,000 particles in SPH simulation. Efficiency of about sort of 95 to 97%. Just comparing that with the results we've been getting from the 24-core, they're approaching those results. We haven't done the specific speed-up tests on it yet, but models that we're running on the 8-core are taking about a third of the time on the 24, so we're fairly confident that that will scale as well. All right, some of the verification type examples. This is just a falling drop. It's 200,000 particles and 10,000 time steps. It took about 24 hours to solve, and you see the droplet falling down there, splashing on the surface. This is called the Rayleigh-Taylor instability. So it's a multi-phase surface tension type problem. You've got oil on the bottom, water on the top, and then air above that. And obviously, because oil's lighter than water, it wants to bounce to the surface, and the instability that results is called the Rayleigh-Taylor instability. This is 500,000 particles and 25,000 time steps. It took about 3 days to solve. And I guess the question is, well, how does this apply to enhanced oil recovery? And this is a prime example of where simulation and enhanced oil recovery can line up. So this is effectively an example of a granular media, so a water flooding of a granular media. The red phase initially is oil, and you've got a flooding phase of water coming down and moving down with gravity. Now, the two examples in A here, you've got a non-wetting water phase, so the water does not really want to adhere to these grains, and you can see that it's actually fingering through and not really washing out that much oil. In the bottom example, it's a wetting phase, so it's adhering to the grains much better, and you've got a significant increase in oil removed through that granular structure. And the aim of this is basically that you can design fluids. So by manipulating through chemical or otherwise means you can increase the wettability of a flooding phase and increase the amount of oil that you're actually washing through the granular media. And it's good to know that on the grain scale, but one of the major benefits of that is the ability to calibrate the larger oil field scale models. So it's not going to tell anyone anything if you can run just a little bit of oil through a little rock, but if you can get better results on the oil scale, you can know where to put your oil wells and where to put your flooding stations and work out the exact yield of oil out of the oil field, then you've got significant advantage in industry. This is just my last example. As I discussed, carbon sequestration and hydrate mining is something that's coming to the forefront of this type of work. The sort of multi-phase, so fluid, solid, liquid type, gas type simulators that you can generate for the enhanced oil recovery type applications, you can also use for the carbon sequestration and hydrate type applications. So firstly, with carbon sequestration, the idea is that you put your CO2 emissions under the ground to reduce the impact on the environment, but obviously you don't want that carbon dioxide to permeate through the rock and release itself back into the environment. So the ability to model that and make sure that it's going to stay put is critical. And with respect to hydrates, there are significant subsea methane deposits, various places such as the Bermuda Triangle, etc. And firstly, from an environmental impact point of view, these subsea deposits can collapse and release that methane into the environment with detrimental effects, and that collapse can also cause things like tsunamis, which is obviously bad for people living on the coastline. On the other side of things, methane is actually an excellent alternate fuel source, so ideally we'd like to be able to mine that methane source and be able to use that as an alternate fuel source. So modelling tools that are able to predict and aid in both of these features are very beneficial, and we believe that the work we're doing at the moment has the potential to be applied in this area as well. So that's all I got today. In conclusion, effectively what we're doing is taking a very complex dynamic circumstance and building simulators to increase the amount of oil that we can actually recover, with the aim that hopefully that should alleviate at least some of the energy crisis we're going through at the moment. Our ability to do that is completely dependent on the computational resources we have at our disposal, and so it's really important that we make the most of the multi-core, because they're talking sort of 100 cores, several hundred core, perhaps 1,000 cores in the not too distant future. Thank you.
Great talk. A question is that how does this approach scale to a reservoir level simulation?
So
or does it?
The grain scale models themselves won't scale to reservoir level. What those reservoir models are is a continuum model that effectively you have calibrated for the different permeability of what you would expect the reservoir rock to do. So you can do continuum models with a particle method, but you wouldn't be scaling the explicit flow through flow through a granular media to the scale. But what you can do is calibrate those models based on permeabilities and calculated quantities like that from the small scale to the large scale.
Any more questions?
Great.
Thank you, David.
Thank you.